In trace evidence, materials found at scenes can be viewed under microscopes. Based upon their optical properties, they can be classified as either isotropic or anisotropic. Isotropic materials have one refractive index, while anisotropic materials have more than one. This picture is of an isotropic material. Under cross polars, the microscopic field of view will be black. When samples are placed on the stage, they will react with the light based on their optical properties. Isotropic materials will remain black, while anisotropic materials will emit light under cross polars. This picture is of olivine, an anisotropic substance. Analysts can use immersion oils to help determine the refractive index of isotropic materials. The first thing that can be done is mount the material in a medium with a known refractive index and observe a backline. Under a 10x objective, a bright halo is observed, and when the focus is raised, the halo will move toward the substance with the higher refractive index. As seen in the picture, there are white halos outside the material. Once the focus is raised, if the backline moves outward, the mounting medium has a higher refractive index. If the backline moves inward, the material has a higher refractive index. Relief can also aid in determining the refractive index of an isotropic material. Relief is determined from how well the sample can be differentiated. The higher the relief or the darker the sample, the bigger the refractive index difference between the material and the mounting medium. This picture shows a darker material, so it has a higher relief. Therefore, the refractive index difference is great. This picture, on the other hand, shows the same substance but lighter. Therefore, the relief is low between anthophyllite and the mounting medium. This leads to the conclusion that anthophyllite's refractive index is close to 1.6. When light passes through anisotropic materials, it splits into two beams that vibrate perpendicular to each other. These rays are deemed the ordinary and extraordinary rays. These two rays allow the sample to be colorful under cross polar. The difference in the two refractive indices is known as birefringence. The picture is an example of quartz under cross polar. It also is anisotropic. Although anisotropic materials are seen under cross polars, they will still turn black at 4 positions when the microscope stage is rotated. These are called extinction points. Extinction occurs when the light vibrates parallel to either one of the vibration directions that either the polarizer or analyzer allows to pass. Extinction occurs every 90 degrees starting at a 45-degree angle. This fiber is not at extinction because it is still seen under cross polars. This is the same fiber as before, exhibiting extinction after being rotated 90 degrees. The first picture has rays vibrating in a different direction than both the polarizer and analyzer. The second picture, however, has a vibration parallel to either the polarizer or analyzer and is therefore at extinction. Another property indicative of anisotropic materials is pleochroism. Pleochroism is when the anisotropic sample changes colors when it is rotated due to absorption of particular wavelengths of light. The color seen is a function of the thickness, chemical, and crystallographic nature of the material. This picture is a comparison of a material that exhibits pleochroism. Under cross polars at one angle, the gem is blue, but after rotation, it is purple. The two light beams that go through an anisotropic sample travel through the material at different speeds. The difference between when the rays exit the material is termed retardation. This is affected by both the birefringence and thickness of the sample. Due to this effect, the analyzer can selectively pass some wavelengths and block others. The colors produced by the analyzer are called interference colors. The sequence of possible interference colors with increasing retardation is presented by the Michael-Levy birefringence chart. Using the Michael-Levy birefringence chart, the sign of elongation of a material can be determined. To determine the sign of elongation, the material is first looked at under cross polars, like this acrylic fiber. Next, a compensator, which adds exactly one order of color, is inserted and is oriented to have a known slow vibrational direction. This is seen in this picture. When the slow direction of the material is parallel to the compensator, the material will undergo addition and experience positive elongation. If the material is rotated so that the fast direction is parallel to the slow direction of the compensator, the material undergoes subtraction and experiences negative elongation. Based off of the Michael-Levy chart, if the color gets brighter, the material has a negative sign of elongation. If the color gets paler, the material has a positive sign of elongation. After the previous fiber is rotated 135 degrees, it changes from first order orange to first order blue. Because it does not move up in order, the acrylic fiber is determined to exhibit negative elongation.